This is section 8.5, and it's entitled Writing and Graphing Exponential Growth Functions. And you can be with me right now if you go to page number 520. All right, page 520. I would highly suggest you have your book open because I will be referring to your book as I make this video. First of all, again, as I always start off, we have some vocabulary we need to know. And today is the first day, probably this year, that we're going to start looking at equations or functions that are not linear. Now remember, linear means straight line graphs. We're going to look at a different kind of function today called an exponential function. So first of all, what is an exponential function? It's a function that's going to have this form: y equals some number a times some number b to the x power. Okay, so you notice that is not in slope-intercept form. Slope-intercept form, if you recall, I'll write it up here. Slope-intercept form, you remember, looks like this, and this is a graph with a straight line. All right. Exponential functions have this form: some number times b to the x power. This number a can't be 0. B in this chapter will always be numbers greater than 0, but they can't equal 1. Okay, so we're going to talk about, for b, any value for b that's more than 0 but not equal to 1. So we could have fractions for b less than 1 or values for b greater than 1. Here would be an example of an exponential function, something like y equals 2 times 3 to the x power. How is an exponential function then different from linear? Well, I think before I show the answer, one obvious difference is linear means a straight line graph. If this function isn't linear, that immediately tells you it can't be a straight line graph. So since linear functions yield straight line graphs, exponential functions will have graphs or create graphs that have a curve to it. All right, so that's the major difference. Exponential functions can either be growth or what we call decay. Growth means we are increasing the amounts throughout the function. Decay would mean we are decreasing the amounts throughout the function. We're going to work on exponential functions today in this section that is over growth, okay, the amounts growing. All right, my pen just froze here for a second. Come on, pen, there we go. All right, so let's go and look at the top of page 20 in your book. And there's two tables at the top of page 20, and one of the things they're going to ask you to do in the homework is look at a table and determine, is the table linear or is it exponential? So how do we determine if it's linear or exponential? So how can we tell if a table's linear? Well, look at the top left table. Do you notice in that top left table that every time we increase 1 by x, which they're showing in the book, that we increase y by 3? This is a linear relationship. Whenever x increases by adding by a certain amount and y would either add or subtract by the same amount each time, that's a linear relationship. It would be like, and you've heard me say this a million times in class, it'd be like me asking you to mow my lawn. That's a linear relationship because if you mow it once, you get 20 bucks. If you mow it another time, which would make it twice, you get another 20 bucks, $40. If you mow it another time, if you add one more lawn mowing, I would now have to give you another 20 bucks, which would be $60 and so on. That is always a linear relationship. And if the relationship is linear, remember, you can always write an equation in slope-intercept form to represent that function. So how can I look at a table and tell that it's exponential? So again, at the top of page 520, the table to the right is an example of that. How can I see that it's exponential? And they demonstrate it in the book. I hope you are looking at page 520. If not, stop the video and be on page 520. So if you look at the top right table, you can see this time as I increase x by 1 every time, y is not increasing by adding or subtracting. Y is now increasing, in this case, by a multiplication. We're always multiplying or tripling the previous amount. So if you look at 2/9 for y, if you triple that, you get 6/9, which is 2/3. They wrote 2/3 in the table. If you take 2/3 and triple it, you get 6/3, which works out to 2, and that's how they wrote it on the table, 2. If you take 2 and triple it, you get 6, and if you take 6 and triple it, you get 18. That is definitely an exponential growth function. So how would I write a rule then for that, a function like that? Well, let's actually do a problem. Let's go to page 524, go to question 4, and we want to determine, is this linear or exponential? So how do we write these rules? Let's go through that. Okay, so in question 4, as I'm looking carefully at it, let me move this over a little bit, I can look at it and I see, okay, for x, I went from -2 to -1, -1 to 0, 0 to 1, and so on. So x is increasing by 1 each time. But now look at y. Let's try adding. 1 plus 1 is 2, but then 2 plus 1 doesn't give me 4. So this cannot be linear. We're not adding the same amount each time. It's not a linear function. So let's try exponential. Let's start with the input, or the output of 1 for y, I should say, the output of 1. If I double that, I get 2. Okay, so that worked. If I take 2 and double it, I get 4. That's working. If I take 4 and double it, I get 8. That's working. Do you notice that every time I increase x by 1, we're doubling y. We're multiplying y by 2. So this is definitely exponential. So how do I write a rule for this function? Okay, and what does it mean to write a rule? It means write an equation. How do I write an equation for this exponential function? Well, the first thing you got to remember is this. Exponential functions always have this form. Y equals a times b to the x power. All right, now do you remember that I said that we were doubling y every time on that table? Well, since you're doubling y each time, the b value, this value right here, is what you multiply by each time on your table. Okay, and I don't know, there's not a term for that. B is what you multiply by each time. So since I'm multiplying each time by 2, b is a 2. So I can plug in 2 for b. Now I got to figure out a. The way you figure out a is kind of what you did. Remember earlier in the year with slope-intercept form? Pretend that you knew the slope was 2, and we had a ordered pair of, I'll just put 3, 8. Do you remember earlier in the year, if you wanted to find the value of b, you plugged in 3 for x, and you plugged in 8 for y, and you calculated to find b. And as soon as my pen stops freezing, there we go, I can show you that. So do you remember early in the year that we just did 2 times 3 would give me 6. I plugged in 8 for y, and I solved for b, and I found out that b has to be 2. So now my equation would be y equals 2x plus 2 for my linear function. I'm doing the same thing here. I found out that b was 2. On my table, do you see the point 0, 4? I can plug in 0 for x, and I can plug in y for 4, and I can use that to solve for a, which I'm going to do on my next slide right now. All right, so I plugged in, you can see I replaced x with 0, I replaced x with 0, and I replaced y with 4, and now I'm going to solve. Well, I know 2 to the 0 power is 1, so I have 1 times a is 4, so that means a is 4, and now I know my equation. It's y equals 4 times 2 to the x power. All right. I can actually, if I want to, I missed a slide, I can actually check that on my calculator. If you type in y equals 4 times 2 to the x power in your calculator and make a table, you'll see that it matches the table in the book. All right. And let me actually do that right now. And I went to my calculator here, and you can see I typed in y equals 4 times 2 to the x power, the equation we made, and I'm going to quickly make a table. And you can see that this table matches the table that was listed on question 4. If you plug in -2, you get 1, just like question 4 said. If you plug in -1, you get 2. If you plugged in 0, you get 4. If you input 1, you output 8. If you input 2, you output 16. So there's the same table as question 4. There's no question that I have that equation correctly done. Okay, so from there, let's do a graphing question. You need to be able to do some basic graphing without your calculator. I would ask you to do an exponential growth function graph without. Very simple to do. I'm not going to try to give you hard numerical problems to do. I just want to know that you can sketch a graph without your calculator. So let's do number 9, and it asks you to graph the function and identify its domain and range. So for number 9, y equals 4 to the x power. Let's make a little table. And the first entry I'm always going to plug in is 0, because if I plug in 0, I always get 4 to the 0 power. Remember, any number except for 0 to the 0 power is 1, so I have that. And now I'm going to start filling out the rest of the table, and I filled it out faster. Let me just quickly go through why it's so easy to fill out a table. If you plug in first power, 4 to the first power is 1. Now remember, if you plug in negative first power, all that means is to take 4, reciprocal it, 1 over 4, and apply the first power. Well, you get 1/4. So if you plug in second power, you get 16. If you plug in negative second power, that just means 1 over 16. All right, if you plug in third power, you'd get 64. 4 times 4 times 4 is 64. If you plug in negative third power, you just get 1 over 64. All right? So again, doing that shouldn't be a big deal, because if you plug in the positive power, and like here, 4 to the first is 4. When you plug in negative first, that just means 1/4. Okay, let's plot those points. So I'm going to do that, and actually before I plot, I forgot to say something. Let's think about our scale here. We got to choose appropriate scale for y's, because if I don't change my scale, 64 is way the heck off the page. So I'm going to make a scale going up by 10s instead of 1s. My x scale is fine. I don't have to change that. So let's start graphing. -2 and a 16th is way almost close to 0. -1 1/4, way close to 0. Then I have 0, 1, which still looks close to 0. 1, 4, 2, 16, 3, 64. And you can see they call this exponential growth. Exponential kind of exponential. It sounds like explode. Okay, when you hear the word exponential, it sounds like the word exploding. Exponential growth, I guess you could kind of think of it as exploding growth. And you can see here, at first, it looks like this isn't even climbing at all, and then once it starts climbing, it basically explodes upward. That's exponential growth, all right? So again, this section is on graphing exponential functions. Exponential functions will always they'll start slow, and then suddenly, once it starts rising, it's going to explode upward, all right? So on these graphs, you're going to have to, on linear graphs, you can maybe plot 2, maybe 3 points max and make a line. When you have exponential functions, you're going to have to graph way more than 3 points, probably 6, 7, or 8 to get a general feel for the pattern. And then you just take your pen, and as best you can't use a ruler for this, it's a curved graph. You just try the best you can, kind of connect the dots with a smooth curve, and like I said, do the best you can on that. All right. How does the value of A affect an exponential graph? Okay, we're going to take our graphing calculator right now. We're going to type in y equals 2 to the x power. Now remember, if you have y equals 2 to the x power, that would mean right now that A would just be 1 here. And we're going to graph this, and then we're going to try graphing 2 times 2 to the x power, 3 times 2 to the x power, and so on. So let's do that right now. Okay. So I'm going to take my calculator, and I'm going to plug in y equals 2 to the x power, and I'll make a graph of that. And I'm just going to check it out, and you can see here, you can see that exponential growth. I got 2 other points in here. Let me pause my video. I'm going to get those out. And you can see that exponential growth here. So let's go back now, and let's see what happens. We'll keep that first graph in there. Let's see what happens if instead of having A being 1, let's plug in 2 for A. So now I have 2 times 2 to the x power. Let's see how 2 affects my graph. Well, as I look at this, I still see exponential growth, but suddenly this kind of explodes up at a faster rate. That's not the correct terminology. Remember, that's called a vertical stretch. We have stretched our graph. Okay, this is definitely stretched our graph a bit. it would have a y-intercept of 2 instead of 1, and my graph's been stretched. Let's try what would happen if I plug in 3 times 2 to the x power. Let's see what that a value of 3 does to my graph. Well, you can see again, this kind of explodes even faster up. The y-intercept would be at 3. This is stretched by a magnitude of 3 in comparison to that first function. Okay? So I don't know that I'm going to go through all those. You can pause the video. What I would recommend you do is try these. Okay? Pause the video now. Try plugging in 4 times 2 to the x power. See what happens when you plug in some negatives. See what happens when you plug in fractions for a, and see what happens when you plug a negative value in for a. All right? A negative fraction, I should say. All right? So pause the video, and are you figuring out how a affects the exponential graph? When you're done, start playing the video again. Okay, so this is the part that I really like about this, because when I think of exponential growth, I think of money. Okay? There's an exponential growth equation, and this is the basic exponential equation, y equals a times b to the x power. But there's a growth equation that we will use, and this growth equation is on page, and I'll write it down here, it's on page 522. And you'll see it near the top of the page, and it's called the exponential growth model, and this is what it represents. Y is the total amount after you include the growth. A is the initial amount that you start with. R is the growth rate written as a decimal. And T is the number of time periods that you're calculating this growth for. Now, you can figure out, and this is probably one of my favorite topics in math, exponential growth, because when I think about exponential growth, if you look at the top of page 523, you'll see the term compound interest. So I don't know how it is for you. I've never met a person in my math class that's ever said, honestly, well, I don't care about money, or I don't like money. Okay? Compound interest is a formula that you can use to find out when you invest money or you put money in the bank, etc., how fast your money will grow for you. Okay? So this formula that I'm giving to you accounts for compound interest. We can use this formula to calculate how money would grow. All right? Compound interest means not only are you getting paid interest on your money that you put into the bank or you invested or whatever, it's also including interest that you make on your interest. And that's what compound interest is, and that's where exponential growth monetarily comes from. If I could teach you one area of algebra that might be a lifelong, hey, I don't care if you want to be a hairdresser, I don't care if you want to be a mechanic, I don't care what you want to be, your money can make money for you if you understand how to do it properly, and it all starts here, understanding exponential growth, all right? So I have just a fun question. I always like to show this question. People are always wowed by this each year. Suppose on the day you were born, your grandparents gave you a gift. They gave you $5,000. You'd probably be happy right now to have $5,000. I would be too. But there was one little catch Grandpa and Grandma put on this $5,000. Okay? This present isn't for you to have whenever. You can't have this money to your 50th birthday. Okay? So your grandma and grandpa said, I'm going to give you $5,000 and you can have it on your 50th birthday. It's your 50th birthday present. So they took the money. They invested it for you. They found a place where this money would gain 11% interest a year. All right? Now, 11% you're not going to get in a bank. The stock market up to now has done that. I don't know if the stock market's going to continue to do that, but there are investments out there that if they put it in the right thing at the right time, it could make you even more than 11%, but we'll go with 11%. If your parents are into finance and things, they might say that's probably higher than normal, but for this example, it shows you why 11% would be a big deal. Okay, so what we're going to do is we're going to find out how much money would you have at age 50. So we're going to use that compound exponential growth model, the compound interest model I just showed you. We need the initial amount of $5,000. we need our growth rate of 11%, and we're going to say that there was 50 years of time periods here, 50 years that you're waiting to get this money. So we have 5,000 times 1. Remember, this is the initial amount here. Here was your interest written as a decimal, and this is going on for 50 years. Let's actually put that in our calculator together. So I have here 5,000 times, open parentheses, 1 plus 0.11, and this is to the 50th power. And at the age of 50, no, this is not a typo, this is not a misprint, you would have $922,824 and roughly 13 cents. You'd almost have $1 million for yourself, all right? You would almost have $1 million. I lost my slide here. There we go. Okay? I'm sure some of you are shocked by that amount, all right? 11% interest is a high rate of interest, okay? Now, one thing I wanted to show you, because I always get questions about this, well, how could that ever happen? That's not real, etc. It is real. I want to show you a chart. This is a real chart. Here's a chart of gold over the last 10 years. Do you see how this gold chart has the same look as our exponential graphs? Okay? And this is just over 10 years. I mean, we can do the math on this right now if we want to. This chart, let me do this right now. Let's take a look at this chart carefully. Okay, look back here on January 1st of 2003, gold was worth between $300 and $400. Let's just call it $350. Gold right now, as of the first of this year, was roughly, we'll say it's almost $1,700. Okay, so imagine someone having, this is, and by the way, this is the price per ounce. So let's just say that you had 100 ounces of gold here. 100 ounces of gold here at $350 an ounce. You would have $35,000 worth of gold. That same 100 ounces 10 years later is now worth $1,700 an ounce. Well, if you take your 100 ounces of gold and you multiply it by $1,700 an ounce, you would right now have $170,000 worth of gold. Okay? So at this rate of growth, can you see how that might be realistic? If I changed the problem I just showed you and I said, okay, on the day you were born, your grandparents bought you $5,000 worth of gold. Well, I mean, if this pattern were to continue, now I don't know if that's going to happen for 50 years, but if this pattern were to continue, it might be very realistic that that could happen. You're already a fifth of the way there just in the first 10 years. Okay? So there is things out there that you can invest in that can make you that kind of money. And that's interesting to see. All right? So that's why I wanted to share that with you. Okay, so anyway, keeping on going here. I wanted to show you one more thing before I stop the video. I know this video's taken some time, but we had a lot to cover. All right? When we have compound interest, it can be calculated in different ways, and I'm going to give you this worksheet, and we're going to be doing this in the next few days, but you can see we can count our interest or compound it annually, which means one time a year, semi-annually, which means twice a year. You have 2 interest payments a year. Quarterly means 4 payments a year. And daily, which means you could have a daily payment. Remember, there's 365 days in a year. That means you'd have 1 payment every day, 365 days. So I want to actually work this problem out with you. Do you see you're investing $5,000 in an account? It pays you 5.5% interest. And you want to find your account balance after 15 years. Okay? So let's actually go and look at how that would work out if we compound our interest annually, semi-annually, quarterly, and daily. Let's do annually first. We're going to use our interest formula that I showed you, the exponential growth model, compound interest. Here's our initial amount invested. There's our interest rate. We're doing this for 15 years. If you put this in your calculator, that works out to about $11,162.38. That's one payment a year. Okay? If you get one payment a year over 15 years, that's how much money you would have at the end of 15 years. Now, if you compound it semi-annually, that means you get two payments a year. So there's a couple things you have to change with it when you write this in your formula. Okay? First of all, you invested $5,000. That didn't change. Your interest rate is 5.5%, but because you're getting two payments a year, you got to break that interest rate in half, because if you don't, it's like saying you're getting 5.5% every half year. No, it's 5.5% a year. So you got to break the payments in half because you're getting paid twice a year. Do you notice now how I have 30? And you might be like, wait a minute, you're only getting paid for 15 years. That's true. But if you're getting paid twice a year for 15 years, does it make sense that twice a year for 15 years means you have 30 payments? Remember, T stands for the time periods. There's 30 time periods you're getting paid twice a year for 15 years. Well, you notice if you compound your interest semi-annually, it gives you just a little bit more money. The more your interest is compounded, the faster the growth. So it's always nice to find that place or that bank or whatever that will give you compounding of interest more than just on a yearly level. If you go quarterly, your initial deposit's the same. The percentage didn't change, but you got to divide by 4 because you're getting 4 payments a year. And now you might be like, wait a minute, it's only 15 years. That's true, but you're getting 4 payments a year for 15 years. You're getting 60 payments. Do you notice how, wow, made a little bit more money? Okay, not way more, but a couple $100 more just because we're compounding more. And finally, if we go to a daily compounding, 365 days a year, you're still investing $5,000. The interest rate didn't change, but you got to break it into 365 payments. And you might be like, what? Where do we get this from? Well, remember, you're getting paid $300 every day for 365 days for 15 years. You got to take 365 times 15. You're getting 5,475 payments. And that works out to $11,408.69. You see, the more you compound, the more you make. All right? I want to quickly end this video with something I show every year. This is neat. It'll take 2 minutes. Please watch this. Again, you might wonder, when in the heck would any of this happen? When could someone make this kind of money doing this? And this video will be a good sample of that.
She had amassed a sizable fortune in her long life, and it was quite a surprise when she left that fortune to a small north suburban college. ABC 7's Teresa Gutierrez had the story.
100-year-old Grace Groner passed away in January. Before her death, she established the Grace Elizabeth Groner Foundation and contributed her net worth to Lake Forest College, her alma mater. The gift, $7 million. It's the largest of its kind in the college's history.
I had no idea it was even possible for somebody such as Grace to accumulate that kind of wealth.
Groner graduated from the college in 1931 and worked for Abbott Laboratories for 43 years as a secretary. She lived in a small cottage in the area. Those who knew her say she was very frugal and did not care about material things. Groner's $7 million estate is the result of $180 specifically issued Abbott stock purchased in 1935 that she never sold.
Neighbors say that Grace lived her life gracefully. She lived in a very private area, and she was private. Although neighbors say that even at 100 years old, she was curious about life and knowledgeable about current events, and that she was great to have as a neighbor.
She was one of the most unassuming people you would ever meet.
Groner volunteered for decades at the First Presbyterian Church on Sheridan Road. Her pastor says she did not have material needs and believed in giving back.
When she was just 12 years old, her parents had both died, and a founding member of this congregation took her in. I think that's when she learned what Christian love looks like.
The money will go to the students to purchase internships and study abroad programs. 34-year-old Erin McKinley, a junior from Lake Zurich, is a student who benefited from Groner's past contributions to the college.
I did benefit from her generosity. She sent me to Jamaica last year for a field school, which was definitely life-altering and changing.
Teresa Gutierrez, ABC 7 News.
All right, so anyway, just to finish that up, a couple of things I could ask you on the video tomorrow. This woman, she left $7 million. Did you hear in the video that this $7 million was accumulated from $180 of stock options? So this started with $180, and through compound interest, she lived to 100 over probably 70 plus years, because she was a secretary, accumulated $7 million. So every once in a while you will hear a fascinating story like that. I'm going to stop the video now. I'm sorry this was longer, but we had a lot to cover.